Welcome to all. This is Raju Murugan. In this video, I would like to give few important steps involving in the computational fluid dynamics. First, I would like to explain few things about CFD, nothing but computational fluid dynamics. Pre-processing, processing, post-processing. These are the different steps in CFD. Pre-processing is nothing but design and meshing of the model, processing, solver setting and running the simulation. Post-processing is plotting, making animation of the corresponding results and contour plots. Today I would like to give a live demo for one CFD analysis using different softwares for meshing, solver setting and plotting. Okay, we'll enter into the video. So first I would like to open a meshing software called Gambit. So I installed Gambit. So here we will open the Gambit and we will select the corresponding folder where we want to make a mesh or like run the simulation. So I will give the browse. So in the F folder, in the CFD tutorial, flow through the 2D pipe. Okay, so flow through the 2D pipe. Okay, so then first I select the working directory for the Gambit folder. So then we will open the Gambit. It will take some time. So before that I would like to tell few important things, software which is available for the meshing and designing. Designing, we can design the model in different 3D modeling software such as nowadays like CATIA is there, ProE, Solid Edge, Autodesk. Similarly for solver processing also there are different software is there like commercial and open source, such as OpenFOAM is the open source software, commercially available software ANSYS Fluent and ANSYS CFX. So these are the software we can use for the solver setting, and post processing we can use in the ANSYS CFD, as well as we can use the Visit, the open source software, as well as we can use TechPlot for the plotting. So this video is entirely for the education purpose only. So I am using like old version of the Gambit and Fluent for learning purpose or teaching purpose to the students. So this is the how the Gambit window will open initially. So I would like to tell few important menu bar here. The first is vertex. Vertex is nothing but the point. So coordinate, we need to create a coordinate. So based on the point we will, like based on our computational domain, we will create a point. I will give the like live demo. Next is line. We need to join the points to create a line. Then face, you can see a line is nothing but the edge, and face we need to connect the edges to create a face. Then volume, we need to connect the faces to create the volume. So today I will give the small simple example of the 2D pipe flow at certain velocity of the air. So we will create the coordinate first, like vertex for the meshing or like domain. Okay, these are the global coordinate system. We can see like origin point. So I will create a one point over there. Then you can see the point. Let's take, I am planning to consider a pipe of 10 mm. Okay, then I am giving y coordinate in the 10 mm. The point is created. Okay, here you can see created vertex 2. The point coordinate system is 0, 10 and 1. So let's fit to the window. We can see the clear 2 points for our system. Then I am planning to run the simulation up to here. The 10 mm, the 100 mm x coordinate is 100 mm. So I like to create a third coordinate for the our model. Okay, I created, then fit to window. Again we can see the flow, the exit point for the flow system is like away from the 100 mm from the starting point. Then we need to create a 0 base for the coordinate system. This is the rectangle flow, because the flow through the 2D is like a simple. So first I would like to give the overall examination like example for the demo. So this is the rectangle domain. Then we created the vertex, first part is done. Then second part, creating the edge using this one. So we need to use the select the point, means shift point, similarly shift. Okay, then you apply, means we join the 2 points. So we need to select the vertex with the shift button, similarly here also, then you apply. Okay, similarly I am doing this also. So now I completed the edge part. Then we need to convert this edge part into the face part to run the simulation as well as to give the boundary conditions. Okay, then we move to the face part. Then I am selecting the edge in the similar manner. 1, 2, 3, 4. 4 edges we can select like this also. Otherwise we can select in, suppose if you have the more edges in your model, then you can pick this arrow mark, enable arrow mark. You can select, see I am unselecting all the arrow marks. So if I want to create a model with all the edges, then you can select this one. We will select easily. Okay, this will be the another method, easy selection of the edges or any other stuff like faces also, point also we can select like that. Okay, then apply. We can see the previously before the creating of the faces, the color of the line is yellow color. Now we clearly see the blue color indication. Okay, right. So then I will give the domain, I mean like boundary condition, zones. Okay, this is in the third option. First is like geometry creation, the meshing. Another is some of the zones for the numerical computation point. Okay, let's like first we need to select the third. Then in this one we need to select the point like lines where we need to give the conditions. Okay, I am selecting this as a velocity inlet. I selected edge 4, we created that as a 4. Then I am creating the velocity inlet. Okay, yeah, velocity inlet. Then we need to change the type to the velocity inlet. Here we have the different conditions over here. Okay, we need to select velocity inlet. Okay, let's select the velocity inlet. The option is in the alphabetic, sorry, in the last. So we need to select carefully for the velocity inlet. Then you apply. Then we can see when the edge is selected and converted into a velocity inlet domain zone. Okay, we can see the label and as well as the color also. We will see the different color for our step. Similarly, then inlet is over, then we need to set for the outlet, right? So I am doing the outlet part. I am giving pressure outlet. Okay, let's carefully select the pressure outlet. Okay, here the option is pressure outlet, yes there. Okay, then apply. Okay, you can see this is the boundary type, velocity inlet. Similarly I will like wait to the window, then we will see some more clear. Okay, okay, then otherwise like yeah, minimize. How to minimize or maximize means we need to hold the right button and we need to drag it up, means the minimize, and down means zooming option. See, I am pressing the right button in the mouse, right hand button in the mouse, and if top movement is zoom out and the bottom movement is zoom in. Okay, to explain to you, these are the two boundary conditions. Then the top side and bottom side has to a wall. Okay, I'm selecting that also wall, shift button and selecting two part because the both are the same wall portion. So I'm giving a wall name is wall, sorry, and we need to select that as a wall only because the pipe, that condition as a wall only. Okay, right, we'll apply over here. Then we can see the boundary condition clearly with different names, what are the names we are given, and which boundary the condition is there, like wall, pressure outlet, like that. So now we created the domain. Okay, there is zones with different boundary conditions. Okay, here we can see. Then we will go to the mesh. Okay, this is a very simple geometry. Directly we'll go to the face mesh. I will like teach you the different types of meshes in future videos because this is very simple domain. Directly we can go to the face mesh and we need to select the face. We have the only one face, then I selected the face. Okay, the mesh element type. Okay, there are different type is available like quad, triangular, quad and triangular combination for the complicated geometry. For the complicated geometries where the circle or like different complex the geometry is there, then we can use the triangle because this is very simple geometry with like element shape like a rectangle. So we can go with chord and the different schemes also available. So I am using the different like default model. Interval size is like here this is the one, means it will divide the 10 unit because this mesh is cut like taking in the unit point. Okay, we are creating here 10 means it will divide the part into 10. Let's see. Okay, interval we will, as of now we will keep this as it is 1. Okay, then we'll see apply. Okay, yeah, this was applied. I already clearly explained you too, right? So I am zooming here. So here we can see I mean for like movement, what we need to do is press the center, means like the roller button will be there, right? Then the press this one and move left and right, top bottom, like this. Okay, so just to explain to you, I am zooming the point where we created. See here we have this has a 10 unit, right? 1 2 3 4 5 6 7 8 9 10. So overall 10. Similarly that will be 100 because we created the 100 unit in the x direction. Okay, right now the creation of mesh is over. Then we need to export this mesh in the MSH format for the fluent solver. Okay, let's do that one. File and export. Okay, here we can see the different option is there: ACIS, parasolid format, IGS format, step, KTIV4 and mesh. So now we are exporting the mesh format. Okay, select mesh and we need to enable this carefully because we are working in the two-dimensional geometry. Here we need to select export enable. Now we enabled. See, export 2D XY mesh. Okay, then we can change the mesh name here itself to get the clear information. Okay, just I am giving 2 underscore dimensional pipe. Okay, like simple understanding. Okay, I am giving this name. Okay, let accept. Okay, yeah, here we can see the menu, here the command box. So what are the commands we did, it will showing here. See, these are the commands we created. Okay, see, successfully we written the mesh, means that means exported the mesh. Okay, file, then I am saving this one. Okay, I saved the command also. Okay, let's minimize this one. Then we will open the ANSYS Fluent for solving. So right now the overall the pre-processing is done. Okay, we'll move to the post solver setting here. Okay, I'm opening Fluent. So these are the very older versions. So I tried my level best because my workstation like computer is very low configuration system. To explaining you, to teaching you, I am using this older version of Fluent. Okay, let's open this one. So here there are different versions there: two dimensional double precision, three dimensional double precision, and only post processing or like full simulation. We are doing full simulation only. Right now we can select two-dimensional double precision. Okay, then run. Means now the Fluent window will open, right? Yeah, it's opened. Here in general we can see different module is there here also: file, grid, define, solve, adapt, surface, head display, plot, all the stuff. Okay, so we need to first read the mesh. Means like here that case. Okay, read the mesh case also same for the older version of Fluent, but whereas the newer version there are the different option is there. Different option means like the naming. Okay, CFD tutorial where I saved here is okay 2D mesh, and here we can see the mesh name where we saved. Okay, then press OK. We are importing the mesh, we are reading the mesh. Here we can see what are the boundary conditions we are given in the pre-processing. Means in the software gambit we can see the different options. So here we can see the number of coordinator elements, that means the code element in the overall domain. Okay, how many points? The top pressure outlet 10, the points zones, how many points is the top and bottom, 200. The overall node is this one. Okay, so these are the stuff. So we will see the mesh. Okay, mesh, the grid, here the name is grid. Okay, so we need to select all the stuff. Okay, then we'll display. So this is how the what we created the mesh. See, we are importing the mesh also. Here the zooming option is different. So each and every software having the different zooming option. Here how we can zooming is we need to press the center and click it down, like increase this one, and just to do the reverse manner. See, that's it. Here we can see the already I explained number of point. Here is like division is 10, here is 100, that is our domain. So here we need to do we imported the mesh. Okay, and we checked also. The first step we need to do is in the grid section we need to check the information whether we are giving the proper mesh to the solver or not. Okay, here it's showing done. Okay, correct. Here we can see our coordinate system which is in the meter. Here we can see x coordinate system. What is the domain? Here the 100. Y coordinate system is 10. Then we can convert this into the different scaling also we can do. Okay, file here. Then we can see size and zones, the number of cells present here and the number of nodes, and all. Here we can see the different details. Okay, define. Okay, then grid. These are the stuff right now. Okay, scale it up. We no need to scale it up because we are using the same geometry. Suppose if we want to convert this into the very small or big, then we can scale it up based on our requirement. Okay, see here grid was created in meter. Okay, fine, that is in the meter only. Okay, here also in the domain. Okay, fine, unit conversion no need right now. Then define the modules, general module, solver and all. So this is the pressure based, like simple cases, so we can use a pressure based software. So the pressure based and different material is there, like axisymmetric cell and 2D and absolute, and these are the different gradient option for the cell, the calculations. unsteady, unsteady, implicit, explicit. These are the theoretical parts. You can like read it from any books or standard books, computer fluid dynamics by Henderson or like that. So these are the different stuffs involving here. So right now we will, for the understanding purpose, we will keep this problem as a steady state problem. Then we will move to the next. Define the first is whatever material is like we are using air only. So the thermophysical property of the air density is 1.225 and viscosity 1.7894 into e power minus 5. Okay, let's, if you want the different models like different materials, I will teach in the future videos. Okay, let's define the two stuff is done. The main important stuff is operating condition is like room temperature, that no need to have the gravity if you want. So we can give in the x direction positive. Y means here we are sending the flow in these directions, so we can give in the y direction also, because pipe flow in axis y this direction 9.81, like we can give that one. Let's define the boundary condition. This is a very important for our problem. Here different zone is there, so we will give the velocity inlet, because that's what's the main stuff, right? Select and set. Okay, I will give for understanding 10 meter per second. Okay, 10. This is also very good initial step. Okay, set at 10 meter per second. Okay, apply and close this one. So boundary condition will set defined. Then what remaining grid interface, these are the advanced steps and units. So units, these are the different units we can convert as a factor. So right now we no need to have this one, like different SI systems also there, like area, meter square or square, like that, acceleration, area, volume. So let's try this one. Oh, no need, like that are all conversion based on your requirement we can convert. So define this is stuff we did, and solve. Okay, solve, control, pressure and all, it will be there. So we will keep this as a standard parameter, and simple scheme, semi implicit pressure linked equations for our calculation. There are different pressure velocity coupling also there, like simple C and piezo and coupled. Right now we will keep the simple. These are the like equations we are going to give the controls for this pressure and all, momentum, all the stuff. So this is right, so we will keep as a default stuff. Okay, fine. And solve, control. Okay, then we need to initialize our solutions, right? Where we need to from, like calculate from, we will calculate from velocity inlet. See here, the automatically the calculation, it automatically taking the velocity inlet. So we need to initialize this one and apply and close. Okay, all right. Solve, monitors. Right now we will monitor only residuals. Okay, fine. Iterations 10. Okay, fine. Plot, right? Oh, okay. Right now we will keep as it is print. We'll see. Plot it later. Solve, monitors, animations. Like then we will do the difference of monitors. Under iterate means we need to setting the solvers iterate the process. Before that, I am trying to tell one more point. Our domain is bigger, so our mesh size we need to reduce, right? So I am going the adapt method here. This will be very useful for many point of view. Adapt the grid adaptation technique, AMR, automatic mesh refinement. So I am trying to here do is like we need to increase the number of cells or reduce the cell sizes. So I am doing based on the region, because region. So I am selecting this is like there are two options there, inside and outside. Here if you know the clear boundary conditions, we can give the x coordinate system, like what's the x and y. Yeah, we can do, we know the like 1 sorry, x 0 to 10 and 0 to 1. Instead of that one, if you have the complex body, you select outside and mark. Here we can see 1000 cells marked for the refinement. Okay, then we'll do the adapt. This is a two-dimensional problem, so it will multiply the cells by 4. Suppose if you are doing the three-dimensional problem, it will multiply the cells into the cell counts into the 8, the 2 power 2 and 2 power 3. Okay, adapt. Let's see. Then it will ask okay for the adapt. Okay, hanging node mode, that is like some technique. I am press yes, then it I already told you, right, the number of cell has to be increased 4 times. Okay, here it's automatically increased, so one more time also we can do because our domain is bigger. So in the calculation it will give some divergence error. In order to get the correct results or stable of the results, then we will increase the number of cells further one more time more similarly and adapt the same process. Okay, now 1600 cells is there, so I will display the corresponding grids. Previously how it was, now how it is. Okay, see, previously it was 10 only. Now you can see number of cells as increasing 4 times. Now it's increasing 8 times. Okay, one more time we will do the adaptation to get the proper good results. Mark means it won't mark now. Why? The reason is the initial setup is only for 2 times, so we need to increase the controls maximum level of refinement into some more point, let 5 or 10, let it be 10. Okay, but we are not going to do the 10 times of increment. Let's try our level best. This is 16,000. Let's try up to 2 lakhs cells. Okay, right, mark adapt into 4 times, 32 64,000, right. Okay, one more time I will do, that will be 64 into 4, it will come. Okay, then more. Okay, then adapt. Yes, right, I already told you that my the process the computer processor is very slow because I am having low memory configuration. Okay, let it be. This is a good count for our cells. We can see the cell count, file grid informations, and see here the number of cells and all. And if we do the check, we can calculate the cell sizes. uh, surface area, this is our points minimum and maximum surface area, and these are the volumes. So let it be. Again we will do the iteration. Before that, what we need to do is a report, define uh, automatic saving, right, solve executed command, initialization, monitors, controls, define, no, not this one, report, no, auto partition, no, file. So okay, before going to that one, just we will export or write one case and data. Okay, let's keep the name as a start. Later we can change the parameters, because I am giving a 10 meter per second. If you want to 20 meter per second, we can change based on this one. And we need to give the gz format for the it will save in the compressed format. Okay, starting case. Okay, let's write the case and data. It writing the case and as well as corresponding data for the future reference. Okay, example, I given the 10 meter per second. Suppose if you want to do the grid independent study, or because that is very important for the numerical work, and or to change the different velocities or different parameters, we can use this dot point. Then we will easily modify the boundary conditions over here. So in the file, write auto service there. Okay, right. So so we need to write every 100 or 50 or 10. Okay, every time 10 time step it will every 100. Okay, uh, where it will save and which format here we can change. Okay, starting otherwise we will give us a uh, sorry 2D pipe. Okay, fine, I set all the parameters. Let me check what is the minimum the mesh size over here. CD tutorial. Okay, pipe, the mesh and case is 7 MB. The data is right now 1 MB. So it will increase the more while calculating. So okay, all the parameters set and I am going for the iteration. Solve, iterate. Here we can see how many number of iterations we need. Okay, let's, I'm giving 1000. Okay, apply and start iterate. Okay, it's calculating, you can see iteration, because our domain is very bigger, so it's saving. Because the 10 iteration was done, so one data is saving, right? This will be very useful for the animation point of view, or to present data in every 10 iterations. We can use this technique. Right now for the demo purpose we will stop up to 100. Okay, 100 time step. Okay, let it run, we'll see. Right now the 20 time step is over. Okay, 30 time step is over. After 100 I will stop the simulations to show you the profiles, different contours of the pipe flow. Okay, let wait for 3 more minutes or like 5 more minutes to see. Now the fourth data also it's saving. Okay, still like we will wait for 3 more sorry 5 more minutes. Before that I would like to give some few important tips to do the numerical simulations. So there are different parameters which affects the numerical simulations, such as grid sizes, grid shapes, and proper boundary conditions, etc. So we need to understand clear physics of the your problem, as well as to get the accurate results and faster results. You need to have the double precision selections in your window, as well as if you are dealing with bigger geometries like bigger computation domains, you need to have the HPC. HPC is nothing but high performance computing facility. Then this kind of problem it will solve within a minute or less than minute. So different case and data are saving. So meanwhile I am opening the some case and data in different another software to show you. The software name is TechPlot. Let it check whether it's opening or not. Yeah, TechPlot opening. So right now the 80 time step is done. Okay, okay, fine. TechPlot 360X is opening. This is like a recent version. All the softwares are only for the teaching purpose, not for the publication point of view. This is just to teach you people. Don't misuse the software, as well as the don't. So each and every file is in 10 MB data after the one. Okay, as of now I will stop where this one solver. Okay, fine. I will cancel the simulations, number of iterations, then I will go to the module and I will change here the automatic save where in the right. Okay, auto save, and I will change this the case uh, here into 100, this also into 100. Okay, let it be. Okay, fine, then let it run because I don't have the proper memory where the solver. Okay, I hit it. Okay, fine, that is enough. Again it will start from the turn one. Okay, before that I will open the processed the saved data. Okay, for the post processing, the software is called TechPlot. This will be useful for the post processing. Here we can do multiple stuff over here. So load data, and where I saved is like F CAB tutorial 2D pipe. Okay, we will select first case and we need to select all the data, right? So because we are not changing the uh, cases every time, so we can select only data for the corresponding data. Okay, then press open button. It will ask we need to uncompress the file in the corresponding folder. No need. If you are uncompressing this, the memory will be more. Okay, no need. No, it will loading in the files. You can see the different cases and data are loading. If you have the good computational facility, you can like do whatever you want, like you can uncompress all the stuff you can do. Okay, done. We'll see how the result is for the just for 10 100 iterations, right? 10 datas. Okay, so this is how the domain is. So I will set into the feet or area. Okay, fine. And these are the different softwares. Here the control also is different. So this is the move button. You can move the domain like it's not it's okay. The stuff, okay, wherever you want you can do. Let it be like this. Okay, before that I will go to the plot and I will fix the axis in this direction. The x-axis like what we kept is 0 to 10, right? No, sorry, 100, the x-axis. Similarly, we don't no need to this select this one like x, and y is nothing but 0 to 10, right? Yeah, 10. Then redraw the domain. Okay, see, we selected the proper this one. So we will select this ticks the marks into the out like downward direction outside. Then that will be easy to visualize. Yeah. Okay, fine. Line we will keep on the top border line also for the better understanding. Yeah, done. Okay, we fixed the proper this one. So we'll select the contours of different contours. So this is the pressure, this is how the initial for the 10 it will be there. We can select a different. Our interest is velocity magnitude, or like this direction is what x velocity magnitude, right? Otherwise we can do the calculate tools, sorry, analyze, calculate variables. Here we can select a velocity magnitude. It will calculate velocity magnitude based on x and y velocities. Yeah, done. We'll select velocity magnitude contours over here. Okay, we'll change this to different regime to give the color indications, the proper color indications. Okay, let it be the legend. We'll keep this as horizontal, but has to be the automatic resize. It will like bring into the proper shape. Okay, let it be. So this is the stuff what we did, and one more stuff I need to increase the time step. I solution time or time. Ampersand into sorry and similar into solution time. Yes, so I will use solution. See here we can see the time. This is the initial 0 time step, right? Hmm. Let me check data spreadsheet data. Okay, it's having all the cases. Yeah, but why it's not showing here? Sorry friends, I'm having some issue to show here. It has to be come file animate. uh, uh Sorry, I will like reload the data. Just for one cases I will explain you. Let's say for 400 open replace data in active frame and reset shell. Okay, we'll select this one, automatically will come to over. No, okay, contour uh, Yeah. Okay. Tools analysis, calculate variables, velocity magnitude. Okay, calculate. Done. Okay, contour, velocity magnitude. Mm-hmm. Next, there is no velocity. Friends, we are having some issues. Okay, let me fix this into the Fluent itself. Then I will export to the. Uh, okay, cancel iteration. Still iteration is going, but in the post process having some issue. Let me check what's the issue. From here itself, display vectors. Okay, field pressure and velocities. Okay, we'll select all the stuff. Display. Friends, it's calculating. Friends, see here, but it's taking too much of time, right? That's calculating, friends. So, like flow is coming outside, it's calculating the velocities correctly. So we need to check. See here, we can see the vector is coming outside as well as the domain is bigger. Friends, whatever we previously shown in the tech plot also correct. Because we need to zoom much more to understand the flow boundaries. So I am loading the data again for the recent case and data 500. So let's take 400 and 500, 2 or 3. Okay, to understanding purpose I selected 3, and but this is a simple method, so it's like saving 3 case and uh, it's loading 3 case and data. You practice, you come to know all the different parameters. So let calculate the velocity, calculation activities like calculate variables, velocity, magnitude. Okay, fine. Okay, let's go to the contour, where it is will be velocity, magnitude. Okay, close, and meanwhile I will skip this axis. Okay, fine. Here we can see velocity is going. Previously also it's going. We'll change few parameters. For here only we will keep velocity vectors and we will plot change the details. Okay. Alright, let's show streamline contour. We will select a particular area. Since the flow is I will select the middle area. I will show the velocity magnitude over here. See, otherwise we can see the different velocity magnitude. This is x direction velocity, y direction velocity magnitude. Fit to window, view, fit data. Here we can see vector. We will remove the vector. Yeah, see, you can see the y direction velocities. Here the flow is happening. Since our velocity is in the same domain, the flow is reached up to here only. It will take certain time to complete the simulations. Yeah, I will plot the streamlines. See, okay, fine. So velocity is coming, so it will take a long time to complete the stuff. Please you keep running your simulations up to like when the solution is converged, so calculation is done, then you can stop the simulations. Mine like I will also run the simulations up to last. We'll see how the results will be. 10 meter per second, right? Okay. For the post processing part, like especially for this one, I will show in the next video. Okay.